we talked about this 2-sat problem, where if I give you a 2CNF formula, there is a 2CNF formula, I want to know, can I assign true versus false to each of the variables so that this whole thing becomes true? So we had this clever way where we could take our formula and convert it into a graph, and we said that if we could find a particular kind of cycle in that graph, then that meant it was not satisfiable. And if there is no such kind of cycle, then this formula was going to be satisfiable. What we actually did here was a reduction, where a reduction in this case is basically just a way of solving problem A by solving problem B instead. So we have a way of taking our instance of 2-sat, and we converted that 2-sat formula into a graph, so that if we solved an entirely different problem on that graph, we had actually come up with our solution for 2-sat. So in this case, we reduced the problem of 2-sat to this like cycle finding problem, where that cycle finding problem we could compute with breadth first search. So in this way, we actually gave a proof about the efficiency of solving 2-sat by relating it to the efficiency of solving this cycle finding problem instead. We knew that this conversion of 2-sat to cycle finding was going to be relatively efficient. Because that conversion from a formula to a graph was efficient, if I had an efficient solution to that graph problem, once I put all of these things together, I had an efficient solution to 2-sat. So this is just a different kind of reduction from what we've seen before. So just like MacGyver had this challenge of opening a door, which he solved by instead solving the entirely different problem of lighting a fire instead, we're kind of doing the same thing with 2-sat. That with 2-sat, we had this problem that we wanted to solve. We didn't quite know how to directly solve that, but we knew that it was related to this other problem of cycle finding, which I did know how to solve with a breadth first search. So that then I could take my cycle finding answer and use that to answer 2-sat instead. This entire path of those 3 arrows became just one slightly more complicated way of solving that 2-sat problem. So in order to make it so that this 2-sat solution was a polynomial time solution, I needed every single one of these arrows to be a polynomial time arrow, to take polynomial time to do. I needed all of them to be efficient. So the idea here is we're going to be using these reductions to reason about efficiency of various algorithms, where in this case what we're going to want is we want this arrow for how I take input to problem A and convert it to an input for problem B, we want that to be efficient. The how do we solve problem B, we want that to be efficient. And we want take solution for B and convert that to a solution for A, we want to make that efficient as well. And we're going to define efficient in such a way that doing 3 efficient things is still going to be efficient. So basically what we've done for 2-sat is given some instance of 2-sat, which is a 2CNF formula, we create an implication graph, which we said was going to be an efficient thing to do, so that if we solved this cycle problem on the implication graph using a breadth first search, whether or not there existed that particular kind of cycle, which was an efficient thing to check, allowed us to efficiently answer this question of, can I satisfy that Boolean assignment? So here I had 3 efficient things, so overall we have an efficient algorithm for solving 2-sat for us, for finding or determining whether or not there are satisfying assignments to this 2CNF formula. So here's how we have used reductions to prove things so far. So when we were talking about reductions for computability, the thing we did with them is we said, let's assume that we have this function h, which isn't computable. And our goal was to show that this new function f wasn't computable by reducing h to f, by showing how we could use an algorithm for f in order to solve h. This is backwards. I'm just going to delete that. Okay. By showing how we could use an algorithm for f to solve h. Which means that if I had some way of solving f, if I finally had that way of solving f, that sort of completes a solution to h. So you can think of a reduction in this case as sort of a partial solution to this problem h, where here we had h, here we had f. So if we said, here's how I could take inputs from h and convert them to inputs from f, so that if I had outputs for f, I could get outputs from h. This is sort of an incomplete algorithm for solving h. Which part is missing? Well, that was how to solve f. If I knew how to solve f, then I now have a complete solution for h. So if I knew that there were no complete solutions from h, and the only thing missing from providing this complete solution for h was a solution for f, then it must have been that I couldn't come up with a solution for f, because that would complete an impossible thing. And when we were doing this reduction for computability, we had to make sure that this arrow for how to solve f was the only missing piece, which meant that these other pieces had to be rock solid. These other two pieces had to be totally computable for that to be the only missing piece. So our caveat for making this reduction happens is the reduction itself, meaning these two parts, that had to do only computable steps. So when we're doing these efficiency reductions, we're showing how we could use an efficient algorithm for some function f in order to build an efficient algorithm for h, which means that if I had some way of solving this problem f, then that was our last step to complete our solution to h. We could have two possible conclusions this time. We have two conclusions that we care about for this sort of reduction, where we said if we did somehow find an efficient way to solve f, then that filled in that last piece so that now we finally do have an efficient way to solve h. So that's what we did with 2SAT. In this case, h was 2SAT, f was cycle finding, so that if I had an efficient solution for cycle finding, that gave me the last thing I needed to find my efficient solution for 2SAT. So if we can do that efficient solution for f, then we're going to have an efficient solution for h. If, on the other hand, I showed that there is not any efficient solution for h, there is no way that I could ever efficiently solve h, then I'm going to be able to conclude that there can't be any efficient solution for f either, because f was the only piece missing from providing an efficient solution for h. So we can use these reductions in two different ways. And kind of like with last time, we had this caveat that our reduction had to only do computable things. In this case, we're going to require that our reduction only do efficient things. In order to guarantee f is the efficient solution to f is the only missing piece for a totally efficient solution, we need to make sure all of the other pieces are efficient. Okay, so these efficiency reductions are these polynomial time reductions. So since our definition of efficient is polynomial time, our reductions needing to be efficient must run in polynomial time. So here we're taking efficient to mean solvable in polynomial time, and this is our formal definition now for what is a polynomial time reduction. So basically, a polynomial time reduction is a function, here it's called r, which maps basically inputs for f to inputs for a problem f into inputs for a problem g, such that r runs in polynomial time. So r is itself efficient, so r runs in polynomial time. And the answer for what function f returns on x matches the answer for what the function g returns on the converted version of that input. So when we've applied the reduction, we've applied the conversion from an instance of f to an instance of g, the answer for that new instance of g matches the original instance for f. And we use this notation here in order to say that f polynomial time reduces to g. So one of the reasons why we like polynomial time as our metric for efficiency is because we do get this transitivity out of it, where if I wanted to chain together a bunch of reductions that are all polynomial time, then the end algorithm that I would get by chaining those reductions together would still be a polynomial time algorithm. That essentially if n to the power c is polynomial, n to the power c is polynomial, then n to the power c to the power k is polynomial. So if we compose polynomial functions, we still get a polynomial, because this is just equal to n to the c times k, which is another integer. So the idea here is if I had some problem f that I wanted to solve, and I didn't know how to solve it, but I knew how to convert it to a two-sat problem, then if I had a polynomial time reduction from f to two-sat, where the runtime of that reduction of r, in that case, was n to the power c, and I had a polynomial time reduction from sat to cycle finding that ran in n to the power k, that meant that I had a polynomial time reduction from f to cycle finding by just kind of chaining this arrow and then back. So basically what's going on is we can just think of this whole path here, this whole path of reduction, as one solution for two-sat that takes n to the power k time. So that now this one here is something that takes at most n to the power c to the power k time, which is still a polynomial. So this is another reason why we like polynomial time reductions, so that we can chain them and still get efficient algorithms. If we define efficiency in this way, then chaining and nesting and embedding polynomial time algorithms within one another still gives us polynomial time algorithms. So just as a recap then about how it is that we do our reductions here, how is it that we're going to do our polynomial time reductions? So the first thing that we're going to do is we're going to start with, so here is the problem A. We're trying to reduce A to B. That is, we're trying to use B to solve A. So we're starting with our instance of problem A. So I'm going to call the input for problem A to be xa. In order to show that A polynomial time reduces to B, first I'm going to pick some algorithm R, some way R, of converting that instance from A, that input for A, into a new input for problem B. I'll call that xb, x sub b, where I need to show that R is going to take polynomial time. So I need that reduction to be an efficient one. It needs to run in polynomial time itself. And I also need this property that the answer B gives for its input is the same as the answer that A would have given for its input. So we need to show that whenever the answer for input xb is 1, that must have meant the input for xa was 1 as well. And whenever the input xb gave the output 0, xa should have given the output of 0 as well. So we needed to make sure the answers matched. Usually, though, the way that we're going to show this is we don't show this directly. We show it by contrapositive instead. So the 0 version, we typically show that by contrapositive. So we're showing that b of xb equals 1 if and only if a of xa equals 1, by showing whenever b gave 1, then a gives 1, and whenever a gives 1, then b gives 1 as well.